Okay, I'm going to work out number 29 and number 39 from page 239. So in both of these, we want to find the maxes and mins using the second derivative test. So the first thing to do is find the first derivative and then use it to find the critical points. So we're going to need to use the quotient rule. So we have the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Okay, we can simplify this. So we can multiply the first two binomials on the top using the FOIL technique, and we end up with 2x squared minus 6x minus 8. And then we can distribute the negative before the last part. We have minus x squared plus 8x over our denominator. So then we can combine like terms, and we have x squared plus 2x minus 8 over x plus 1 quantity squared. And we can actually factor the numerator into x plus 4 times x minus 2. And then we have that over x plus 1 quantity squared. So there's our first derivative simplified. To find the critical points, we want to see what makes this equal to 0, so set the top equal to 0. And we want to see what makes it undefined, so set the bottom equal to 0. Okay, so when we set the top equal to 0, guess I don't need those parentheses, do I? We end up with x equals -4 and x equals 2. And when we set the bottom equal to 0, we end up with x equals -1. However, if you look back at your original function, -1 would make the denominator 0, so -1 is not in the domain of the original function, so it's not going to be a critical point either. Okay, so these are the critical points, and what we want to do is figure out if they are maxes or mins or what, and we're going to do that using the second derivative test. So that means we need the second derivative. So let's go ahead and find that. So starting with the first derivative, now I'm going to use the version of the first derivative that I had before I factored the numerator. And then we're going to use the quotient rule. So we have the bottom times the derivative of the top minus the top. Remember, ho-de hi minus hi-de ho over ho-ho. Got to get that diaphragm working in there. Times the derivative of the bottom. Now, for the derivative of the bottom, we use the chain rule. So we have 2 times x plus 1 to the first times the derivative of x plus 1, which is just 1. And this is over the denominator squared. Okay, first of all, if we're going to simplify this, notice that we have an x plus 1 here, we have an x plus 1 here, and we have some x plus 1s here. Let's cancel an x plus 1 from each of these parts. We have part 1, part 2. So if we cancel 1, then we're just going to have 1 there. We're not going to have that one there, and this will be a 3. I don't really like showing my work that way, but I don't have a whole lot of space. Okay, so what do we have left? We have x plus 1 times 2x plus 2 minus 2 times x squared plus 2x minus 8 over x plus 1 quantity cubed. Okay, so let's go ahead and simplify the numerator. Technically, we don't have to do all this simplifying because what we're doing with it is plugging in the number -4 to it, and we're plugging in the number 2. So we could plug it in without simplifying, but I think that's a little dangerous. There's a lot of room for error here. Room for error either way, I guess. Simplifying, there's a lot of room for error too. Okay, so I'm going to multiply these together by the FOIL method, and that gives me 2x squared plus 4x plus 2. Oops. And then distribute the -2, and that gives us minus 2x squared minus 4x minus 16 plus 16. Oops. Okay, and this is all over x plus 1 quantity cubed. So notice that we have 2x squared and minus 2x squared. we have 4x and minus 4x, so all we have left on the top is 18. So our second derivative is 18 over x plus 1 quantity cubed. So the second derivative test is where we take each critical point and we plug it into the second derivative and see if it turns out positive or negative. So let's take negative 4. F double prime of negative 4 would be 18 over negative 4 plus 1 quantity cubed. Negative 3 cubed is negative. So this would be less than 0. It would be negative. And remember what that means? That means that the function is concave down there. And so that means we have a maximum there. So that we have a local maximum at x equals negative 4. Then we do that for x equals 2. Take it, plug it in the second derivative. Notice that gives you a positive denominator, positive numerator as well. So f double prime of 2 is positive. Remember what that means. That means the function is concave up, so you're at a local minimum. Okay, so that takes care of number 29. And now let's take a look at number 39. So we're doing the same process where we're figuring out, actually we might have more to do on this one. I think we also need inflection points. I didn't look in my book, but it looks like I found critical points, I found concavity, I found inflection points, and minimums and maximums. And the function was f of x equals x cubed minus 2x squared plus x. Okay, to find critical points, we find the first derivative, 3x squared minus 4x plus 1. And we're going to set that equal to 0. And this does factor into 3x minus 1 times x minus 1. Set each factor equal to 0. And solve each one. And you get x equals 1/3 and x equals 1. So those are critical points. Okay, now what we want to do is, well, we can kind of do two things at once. So we want to find inflection points, so we need to find the zeros of the second derivative, and we want to know if our critical points are maxes or mins, so we need the second derivative for that. So for both things, we need the second derivative. And it's easy to find the second derivative for this problem because it's just a polynomial. So looking at the first derivative, the second derivative would be 6x minus 4. And we set that equal to 0 to find the pips, I like to call them, the potential inflection points. We get 4/6. I always find that hard to say, 4/6. And then we reduce that, and you get 2/3. So that's the potential inflection point. We don't know yet if it's an inflection point, so that's why I gave it the name potential. Okay, so now what we want to do is take the number line and divide it into intervals, splitting it at the pip, and we're going to check out the concavity on each interval, see if there's a change in concavity. So what we do is we take a number from the interval and we plug it into the second derivative. We see if it turns out positive or negative. Well, here's where we want to do two things at once. Remember how we have these critical points and we want to know whether or not they're maxes or mins. So if we could plug them into the second derivative and look at the sign, then we would know. And we also are looking for a number between negative infinity and 2/3 to plug into the second derivative. So how about if we just use 1/3? F double prime of 1/3. Make that a little bit more clear. 1/3. Okay, so if we plug 1/3 into the second derivative, 6 times 1/3 minus 4. 2 minus 4, that's negative. So that tells us two things. That tells us that f of x is concave down. And so that also tells us that that point is a maximum. And now we'll do it again for something in between 2/3 and infinity. Let's use 1, because we needed to know if 1 was a max or a min anyway. So let's plug it into our second derivative, 6 times 1 minus 4, and that's going to be positive. So that tells us that f of x is concave up. And it also tells us that we have a minimum. Okay, so since there's a change in concavity, we do have an inflection point. So x equals 2/3 is where the inflection point is. And then because we had the negative second derivative at 1/3, x equals 1/3 is a local max. And then we had the positive at 1, so x equals 1 is a local min. Hope that helps.